Hello, good afternoon. This is the opening of Thrust Area 4 and the detection of undeclared activities and inaccessible facilities. And I'll be using my mouse to point to things. So we're very fortunate in the detection, and for a particular thrust area, we have an NSA Roadmap for ground-based nuclear detonation detector. And it's fairly current, 2014. And our thrust area has three of the main technologies. It has seismology. I'm going in the order of speed of signal propagation. It has infrasound, and it has radionuclide. We had two gaps. We don't have hydroacoustic in our group. We also don't have speed of light technology in our group. So we would very much like to identify people that can cover those gaps, because at the end of the day, it's all about bringing it all together. And I recommend anybody who has questions about detection of nuclear explosions or any explosion to the document that's referred in this slide. In terms of challenges and gaps, we have two treaties we're going to concentrate on. There is also the Fissile Materials Treaty that Paul Wilson can meet, but mostly Comprehensive Nuclear Test Ban Treaty. And they are interested in having more participation also in the CVT. I was, in fact, in Vienna yesterday and earlier this week for an Infrasound technology workshop. And they were very happy to hear of the progress that the CVT is doing and their topics of interest. In particular with Paul Richards' reanalysis of the May 2010 event. And the other one is the Treaty on the Non-Proliferation of Nuclear Weapons, the NPT. And the IAEA also met with their foresight expert on Tuesday. And the additional protocol allows us to develop and deploy equipment. And one of the implementations that they had was the ability to use ground-based robots to survey facilities. So when you develop sensors, think kind of Roombas, essentially little drones rolling on the floor, and having your sensor as a payload to roll around. So what are we trying to do for the ground-based and CTBT? We want to detect and identify even smaller nuclear test explosions. And right now, the international monitoring system of the Comprehensive Test Ban Treaty is fully armed and operational. This system can deliver what we promise. And at the Science and Technology Workshop, it was stated, yep, the scientists have delivered. It's a political problem. We need to ratify it. So we're there. But if we start looking at the smaller and smaller events, things get a little bit trickier. There's a possibility of us interfering with the legitimate activities, industrial or otherwise, of nations. And so this is a dialogue that Paul Richards is going to bring up in his presentation. And it's not about certainty, it's about what level of risk is acceptable. And so uncertainty management is it's a real issue, in particular for source identification. For topics like seismology and infrasound, we can kind of, location and time, it's okay, but the ID, what is it? That has a lot of room for interpretation, and we need to develop better algorithms and also real-time processes for identifying sources. Data collection under the additional protocol, and also the concept of site inspections. This is where we have some room for the NPT. This is where we can set up not only spot measurements, but also persistent monitoring systems. And again, the aim is to detect undeclared activities and facilities. I'm going to run a little bit quickly through this. This is the International Monitoring System, all technologies. And I'm not going to show the hydro because we're not covering, but if you look at the most well instrument is the seismic network. These are the globally distributed seismic network that are part of the global network, as well as the international monitoring system. Infrasound, it started, the deployments were in 2000, so we have 15 years worth of growth in that, and this is the first ever global infrasound network. And it's, again, mission capable. And this is all the radionuclide stations in the world. And we run 2 stations for the CTBTO, the station in Hawaii and in Palau, so we have access to some of this information live. We have a great team on the detection side on the T4. The whole CVT is full of talent, but these are the folks that I feel like I have to learn more about. And I want to also thank Paul Richards for leading the thrust area over the fiscal year 15, this last year. And then this year, somehow I'm doing this. So I'm putting together and learning a lot from my colleagues. Thank you. And so I'm doing the infrasound and also kind of learning about our group and how we can bring everything together. John Lee is doing the radionuclide atmospheric transport. Abby is developing detection systems for radionuclide. And Paul Wilson and Megan McGarry are doing the simulations of fuel cycles. And here's our proposed objectives for fiscal year 2016. So we started with identifying possible gaps and challenges in CTVT and NPT for monitoring verifications. And we'd like to start looking at monitoring both spot and persistent and forensics, including attribution, which is a very delicate topic as it involves source identification. And once you decide that something is indeed nuclear, where did it come from? It takes too long to do that right now. And part of that is because our networks are sparse still for our applications. Some of it is because the problem is complicated. So we want to expedite this. How quickly can we deliver a source identification that is usable for real, national and international security challenges? And so we want to also incorporate speed of light technologies such as particle detectors and imagers. And that's kind of on the technical side. Almost more importantly, we have to understand the source and boundaries to data sources, and also the monitoring agencies that we serve. Some of them are bilateral, we can exchange information. Some of them are diode-like, information only goes one way. And we have to understand what those limitations are. Also, establish the trusted routes to access limited distribution data, such as the IMS data for the CTVT and radionuclide data. And if we are going to inform back, we need to have those routes clearly established and what are the protocols for them. And ultimately, we're here to build a workforce. This is what the CVT is about. And we should be able to build the technology and the skill set to address real-world national and international security challenges. I'm going to move as the signal propagation speed goes. And so we don't have speed of light technology. If you're close by, you can get it instantly. Or if you have satellites, you can get them according to the orbit cycle of that particular imager. The next one is the speed of sound, or speed of seismic velocity. And that will give you, this is the most established technology for our monitoring technologies. And Paul is going to do a reevaluation of the, talk about the May 2010 event near the North Korean test site and how he can improve source identification. Again, the ID becomes sensitive, and it's a crossing of cultures in some ways. You have a lot of expertise within the earthquake monitoring community for natural hazards, and then you have a different skill set with the national security concerns, in particular when it comes to international events. And then he has a new approach for locating large numbers of earthquakes in the oceans and on land. And the figure that I'm showing here is a reanalysis showing explosions on one side, on what you see on the left-hand side, so chemical and nuclear. And then on the right-hand side, there are earthquakes. The two red squares are the recent nuclear tests in North Korea, and the green square is the May 2010 event, which is much closer to earthquakes than to nuclear events. So I'll let Paul tell this story. It's a really good story, and it took 5 years to unravel. And there's going to be a discussion and a debate of the May reanalysis. And also, there's an impact to be able to identify the smaller events. And so one of the things that Paul has been doing is data rescue. We have a lot of legacy events that would never happen again. And so he's taking that data and digitizing it and making it available. And again, uncertainty reductions. But I want to bring up that a lot of this treaty monitoring is an international, global network type of problem. And we all have the same problem: sparsity and denied access. In particular, for the May events, we didn't have access to certain data sources in China that queued some of these events. So solving and addressing these problems of sparsity and data access are one of our primary challenges that we have. Moving on to infrasound, I'm going to take a little bit longer here just because this is my one window to brief for infrasound. On the left-hand side are legacy systems. On the extreme left, this sensor here, it's circa 1999, and it's still in operation. It's still fielded in various stations, Palau and Dio Garcia. And the digitizer, it's a 24-bit digitizer, big chunky things. They're still running on Windows XP. On the right-hand side here, this guy where the arrow is, that's what we use in the US. Right now, in the Hawaii station, that's what's being out there. So again, this is circa 1999. And the next generation is this big boy over there. For regional studies, we deploy smaller digitizers that don't have authentication, all those layers, and then smaller sensors. And they're just cheaper by factor of 2 to 5. On the right-hand side, this little guy here, the silver, looks like a garbage disposal, replaces both of these things right here. It's a 24-bit digitizer with substantially improved dynamic range and sensitivity. So this is the next generation. And this is like IMS grade digital sensor with high sensitivity. And on the low end is the supercomputers that we have in our pockets. So we can all record infrasound right now. And these are all 24-bit digitizers. The new version of the app is 24-bit. It has all the communication built in. So this is like a smaller version of that. And of course, this one costs $13,000. This iPod Touch cost me $200. So it's not as sensitive, but that's just now. Maybe in 5 years it will be. So I want to introduce that this is what we're going to be concentrating on for a project. And of course, infrasound, there's an app for it. Any of you can go to the App Store, type infrasound. There's only 2 apps. They're both ours. Download them, push play. You're recording, streaming, and processing. It makes it very easy. So the whole concept of denied access, and any of you who are familiar with maritime security in the Asia Pacific region probably recognize that this is a substantial issue. This breaks a little bit of those boundaries. Once we have numbers and we address the issue of sparsity through low-cost ubiquitous system, we are in the world of machine learning and data mining. And we're building that. We're building the cloud. So cloud architecture is a very interesting topic right now, and we're building within that framework. Right now we have iOS because they have configuration control, and we had an unfiltered data path. But we have finally traction with Google Android team. They're going to build a special capture path for us for low data unfiltered development. So probably by next year, we'll have an Android app which will open capture in all of Southeast Asia or the whole Asia Pacific region. And back to the subject of denied access. The Tianjin harbor explosion of 12 August 2015. It's a very transportable problem. In maritime security, harbors are very vulnerable places. And after something explodes, your first question is, what type of explosion was it? What kind of contamination issue do you have? How do you assess that as quickly as possible? Do I send in tanks or do I send emergency systems? So how quickly can you establish that and issue a response and de-escalate a problem? Because do you respond in a military way or do you respond in a civil defense way? You need to shorten that. We need to shorten as a community. And so part of that is source and signature characterizations. Again, going to CTBT and NPT, are the activities in a nuclear facility legitimate as reported? Are there variations from these activities that you can infer from the background noise of the turbines or the various industrial machinery inside of that? This is a tractable problem. And so our collaborations with the Idaho National Labs, it was fantastic. There was all these incredible noises out there. And some of them, we didn't even know they were there until we measured them because they're not within standard. So we found many things, and those fans were, that was it. That was one of the main signatures. And you don't have to be in the facility to measure them. You can be over the horizon, 10, 20 kilometers away, and pick up the signatures because everybody needs to breathe. And ventilation systems and cooling systems need access to the air in there. So we have a way to perhaps penetrate some of these boundaries. We also have collaboration with Sandia National Labs looking at sensor characterization Even on a different, under DTRA, we're part of sensor evaluation. And so this dovetails very well with NNSA. Lawrence Livermore, we're working with them on the big data problem. They have done great jobs on the mining of the IMS data, also at the really large scale levels. And so Anthony Christe, my graduate student who's here now, he's going to be spending some time in Lawrence Livermore in November and pushing forward in this collaboration. And of course, we have contracts with the CTBTO, a good relationship with them, and more importantly, its signatories. This is an international problem. And a lot of times, getting access boils down to personal relationships with individuals. And you need to keep that alive. So in terms of event reevaluation, Julie Schnorr, back here, she's working on the Tianjin event reevaluation. And on Tuesday, just this last week, all this data showed up in China. The South Koreans picked up some nice infrasound data, but none of this data is in the infrasound domain. So the best I can do is ask very nicely, could we please have access to the data and collaborate? And slowly but surely it's coming in. And Julie's going to talk a little bit more about that. And part of the aim is to improve detectable yield and energy resolution. So these are some of the infrasound stations on the Chinese network. So you can see Tianjin's got a signature, and I looked at it just 2 days ago, and I have a report on that. And so we're going to try to work with the folks over there to either get the data itself or get a product that's usable to us. And we do have some open networks in Beijing, and Dr. Richards also worked a little bit on this event, and they picked it up very nicely, just coupling into the ground from the atmosphere. And again, Julie will be talking about the reanalysis later on. So moving out of infrasound, outside like a broad scale summary of what we've done for this last year and what we intend to do next year. We have a radionuclide atmospheric transport. And I would like to congratulate John Lee because he actually got the IMS radionuclide data. And today I heard the news that he got the radio xenon data also. So he figured out the vehicles. This is really key. And so now it begins on how do we keep expanding that network, how do we work with NDCs to have a relationship of data collaboration, exchange, and provide information back for event reevaluations. And so he's also doing atmospheric transport modeling, using some of the standards and also doing benchmarking with those, and more advanced signal processing algorithms for data simulation and synthetic data production. And so again, we've got data for Fukushima. And once you open those floodgates, then you have the ability to do also forensic analysis and hopefully reduce the time between events and data access. So for the coming year, the benchmarking on the transport cords will continue. Transport cords are very sensitive. Same thing as we have with all technologies. Data sparsity is a problem, in particular over the oceans. And so we need to really validate these. And going back to the source, how do you figure out, how do we construct the source and go even back to attribution? And uncertainty management is a key topic for all of us. Certainty is a fiction. It's something that comes with religion, not with science. So we just want to know how comfortable we are with our solution. And again, develop methods that are systematic, reproducible, and transportable. Now, Abi Farsoni in Oregon State, he is going to address improving the energy resolution of the radioxenon sensors and also address memory effects. Oh, I have 2 minutes left somehow. So this is out of the 25. I'm just burning.
20 and then 5 minutes for questions.
Oh, okay. I might cut a little bit in the questions. All right, so Abi's working on the detector side, and he has 20 minutes to present this, so I'm not going to go into the detail of any of these presentations. The main thing is I started to benchmark it, compare it with models and data, and this is a very nice development, and trying to make it smaller, more power efficient. Ultimately, there's not enough radio xenon detectors in the planet right now. It's way too sparse. So if you're going to solve these problems, you're going to need more of them. So I recommend that we start working on also the whole digitization and transport, so make it something that has a little bit more density. And so this is one of our challenges, and comparing this with other radio xenon isotopes is something that he's already initiated. And again, improve the system, make it faster, and lower power consumption with higher sensitivity. The Paul Wilson and Megan's group, they're the most transportable of our projects because we have to wait for the signal to arrive here. Their group, if you have a detector on site and you get a speed of light, you're ready to go. You can start, you don't need to wait for a signal to arrive. And so they're working on doing modeling for both the highly enriched uranium, looking at different scenarios for production and possible diversion. Also looking at anomaly detection. This is an example with low enriched uranium, and looking at the statistics reported versus perhaps observed. They're using synthetic data. And the one on the right I thought was very intriguing because you have two smokestacks that are continuously producing, and they're using a krypton as a tracer. And then you have an undeclared facility somewhere in the middle who basically pumps in for a while and eventually fades to the background. And they're assessing how detectable some of these undeclared facilities might be. Again, they have good overlap with other trust areas, so they're working with the T2 for data mining, and with also for a group with the very nuclear release. And they're looking for other ways to integrate other groups, in particular with the nuclear facility simulation, which nuclear archaeology, how cool is that? I didn't know that was a thing until I started working with Paul. So looking back in time, this sounds like forensic studies a little bit too. So again, the interdisciplinary collaborations and also the social aspect of socio-behavioral models. And back to signatures. How do we get correct attribution? Delicate topic, but very important. And again, going back to what we're trying to accomplish, not just identify and fill the gaps, but also to build communication routes with the agencies that can most use these information, and to build a skill set, a workforce that can address these needs for real-world national and international security challenges. Thank you.
And I think you're probably all aware that the NSA Laboratory's primary mission in life is nuclear weapons. So as an adjunct to the other side of that coin,